Hello guys, welcome to the channel. In this particular video, I am going to talk about a very interesting concept which is topological sorting. So this is really important and interesting concept which is asked by companies like Amazon, Microsoft and Flipkart. So let's see the introduction. Okay, so here it is. It says that topological sorting is defined as the arrangement of nodes of a graph in such a way that for each pair UV, where we have a directed edge from U to V, U comes before V. Let me explain with this example. So here we have a graph which has three nodes N1, N2 and N3. Now for this, whenever we have a pair like let's say I'm talking about N1 and N2, here we have a directed edge from n1 to n2, right? So I will write the arrangement like n1 and n2. Now we have n3, right? So how to write n3? Can I write n3 here? If I try to write n3 here, then you can see that we have a pair n2 n3, and there is a directed edge from n3 to n2, right? So this. Now this is something which is wrong. We have to write always n3 before n2. Why? Because we have a directed edge from n3 to n2. So arrangement should be n1, then n3, then n2. Now if you check any edge, for example, we have a edge from n1 to n2, so it will be like this. We have a edge from n3 to n2, it will be like this, and we have a edge from n1 to n3. So now you can see that whenever we have a edge from u to v, then u always comes before v, right? So this is what the topological sorting is. Now there is one more important point, which is this one. It says that if there is a cycle in a graph, then topological sorting is not possible. Why? Let me take an example. So if we have n1, then I have n2, then I have n3, and then I have cycle like this, right? So there is no possible way to write n1, n2, n3 in such a way that it always like u always comes before b, like this one, right? Why? If I try to write n1, then n2, then n3, then you can see that we have an edge from n3 to n1 again, and this is something which is not able to be resolved. So this is where we are never able to write the topological sorting for a cyclic graph, right? I hope you have understood this thing. So we are always going to have topological sorting for directed acyclic graph. Now the question arises is, why topological sorting? Let's see. So there are multiple applications of topological sorting. I have written few of them. The first one is data serialization. The second one is finding cycle in a graph. And the third one is removing symbol dependency in linkers. What are linkers again? If you guys are aware of the compilation process, then you will surely know about the linkers, right? Fine. Now, what are the algorithms to implement topological sorting? There are two algorithms. One is based on BFS and the second is based on DFS. This particular algorithm is known as Kahn's algorithms, and I am going to explain this particular algorithm for this video. Now, let me move to the problem statement. So here is the problem statement. It says that you are given a directed acyclic graph with V vertices and E edges, and you have to find any topological sorting of that graph. Can you notice one thing here? What does this mean? Find any topological sorting. Let me explain this. One important thing is whenever we have a graph, so let's say I have graph n1, then I have n2, then I have n3. Let's see whether I can explain this thing for the this particular graph or not. So one possible sorting is n1. Okay, even let me remove this edge. Let me remove this edge. So one possible topological sorting is n1, then I have n2, then I have n3, right? Because from n1 I'm going I have a edge to n2 and I have a edge to n3, right? What about this particular arrangement? I have n3, then I have n2, then I have so let me erase this. What about this arrangement? I have n1, then I have n3, then I have n2. Is this a right topological sorting? So from n1 I have n3, from n2 I have from n1 I have n2 as well. So you can see that there are two possible topological sorting for this particular graph, right? This means that for any graph we have multiple arrangement possible. So it is saying that you have to find any topological sorting of that graph, right? Okay, so one graph is given here. let's try to write a possible topological sorting for that graph. For this graph, uh, one possible arrangement can be, I have 5, from 5 I have a h to 0, right? And I have an h to 2 as well. Okay, and what about this 4? From this 4, an edge is going, okay, so from this 4 I have 1 edge to 1 and then 1 to 0. So I have 1 to 0 and then one edge which is going to 1. Let me write 1 here. Okay, what about this one again? From this one I have one edge which is going to 3, so I can write 3 here. Okay, so am I left with anyone? 1 2 3 4 5 6. 1 2 3 4 5 6. So you can see that this is one of the possible topological sorting. Okay, what about 2 3? So from 2 we have a edge which is coming to 3, so there is a problem. From 2 we have a edge which is coming to 3, right? So I can solve this. What I can do is I can write 5 4 0 1 2 and 3. So what about this one? What I can do is I can check, from 5 we have a h to 0, from 4 we have a h to 0, and what about from 5 to 2? Yes, we have an edge. And what about from 5 to 1? Okay, what about from 2 to 3? 2 to 3 we have edge, and for 4 to 1 we have an edge, right? So this is one of the possible topological sorting, and 1 is given in the output here. So you can see that this is also possible. We have 5, 4, 2, 1, 3 and 0. So for this we have edge from 5 to 0, then we have from 5 to 2, then we have from 2 to 3, then we have from 4 to 1, right? And then we have 4 to 0. So you can see that this is also a particular possible topological sorting. So I hope you have understood the problem here. Let's talk about the solution. For the solution, I have written the same example which is given in the problem statement, and we are going to solve this problem with Kahn's algorithms again. Kahn's algo, right? And for this algo, I want to start with explaining the intuition behind this algorithm, right? So let's see. Let's see. We are given this graph. For this graph I want you to notice one thing, that okay, it comes from the definition of topological sorting. It says that whenever we have a directed edge from u to v, then u must come before v, right? So I want you to notice this particular node here. For this node we have an outgoing edge from 5 to 0. We have one more outgoing edge from 5 to 2. We don't have any incoming edge, right? So can I write this 5 at the first place? Yes, I can write, because before this 5 I don't need to write any like any u, because there is no any incoming s to 5, so 5 cannot be v in any case, right? Okay, and we have any other node like this? So yes, we have this 4. For this 4 again we have like no any incoming s to it, right? So I can write 4 as well at this second place. Even we can write 4 and 5 as well. This is also possible ordering. Now I want you to notice one thing, that the sorting or the arrangement of the nodes depend on the number of nodes incident. Okay, let me write incident on any node. I think instead of nodes I have to write a number of edges. So this is something that is very important, and this particular thing is known as in degree of a node. In degree of a node basically means that the number of incoming edges, right? So you can see that there is no any incoming edge for this 4 and for this okay, for this 5 and 4. So this means that we can write one observation, that the arrangement depends on the arrangement of the nodes. You can also say that the arrangement is nothing but the topological sorting. So the arrangement of the nodes depend on depends on in degree, right? Okay, so now I can show you the algorithm. Here is the algorithm. It says that the first step is to store the in degree of every node. The second step is to create a queue, and then the third step is to initialize the queue with all those nodes which have 0 in degree, right? You can see that I'm actually printing those nodes first which have 0 in degree. You can see that. So Okay, I'm also going to show you the dry run, but before this, let's see the algorithm. Now, this is the point from where we are starting performing BFS. While queue is not empty, we are going to get a node. After this, we are going to store that node to answer, and after that, we are going to check every neighbor, and we are going to reduce the in degree by one, right? And if the in degree becomes zero, then again we will store in the queue. What does this mean? The intuition behind reducing the in degree by 1 is, once I have printed this 5, then the dependency due to this 5 on this 0 and 2 will be removed, right? Why it will be removed? Because after 5 we can print this 0 and 2. This is what it means. So I can remove the dependency due to this. Once the dependency removed, so you can see that now the in degree of this 2 has become 0. So after 5 we can print 2, right? This is what it means. And we still cannot print this 0. Why? Because the in degree of this 0 is still not 0. Once the in degree becomes 0, then we can print. So 5, 4, 2, this is how we are going to move. Let me remove this. I'm going to show you the try run now. Because once the task is done, all we need to do is to return the answer, right? Okay, so now let me show you the dry run. Dry run is quite simple. First of all, I'm going to store the in degree. So there are what are the nodes? 0, 1, 2, 3, 4, 5. Let me write the in degree of all the nodes. I'm going to change the color here, and you can see that the in degree of 5 and 4 is 0. In degree of 2 is 1. In degree of 3 is 2. In degree of 0 is again 2, and in degree of 1 is 1, right? This is what the in degree looks like. Now what I can do is, first of all, I can store all the nodes with in degree 0. So I have a queue here. In the queue, I'm going to store 5 and 4. These are the first nodes that I have stored. And now if I start performing BFS, then first of all, I will pop this 5 out and I will store in the answer. This is the answer. I'll store in the answer. Once I have stored in the answer, then I will reduce the in degree of the neighbors by 1. So now the in degree of 2 has become minus 2 minus 1, which is okay, 1 minus 1, which is 0 now. And the in degree of this 0 has become 1 now. Now I will again check the same thing. If the in degree is 0, then store in the queue. So I'll store 2 in the queue, and this 5 is now popped. What about this 4? I will again pop this 4, and once I pop this 4, after this I will check the neighbors of 4. So the first neighbor of 4 is 0. I'll reduce the in degree of 0 by 1. So now it will become 0, and I will store 0 in the queue, right? This is queue. And what about this one? For this one, we already have the in degree as 1. So if I decrease by 1, then it will become 0. And this way, I will be able to store 1 in the queue, right? Fine. So now I'm done with 4 as well. Now I will come to this 2. I will pop this 2 out. And once I pop this 2, then I will reduce the in degree of this 3 by 1. So now it will become 1. And I will print 2. And after this, I'm done with 2 as well. Now I will come to 0. So for 0, there is no any neighbor. So just simply print the 0. What about this one? For this one, we have one neighbor, which is this 3. And the in degree of 3 is 1. I will reduce by 1. Now it will become 0. So once it has become 0, I'll store 3. And I have not printed 1 yet. So let's print 1. At last, I will come to this 3. There is no any neighbor. All neighbor are processed. So just simply print 3. This is what the possible topological sorting of this graph is, right? So once you have written the topological sorting, just return the answer. This is the last step that we have. Now I hope you have understood the concept of Kahn's algorithm to find the topological sorting. Let me show you the code. So here is the code. On the left hand side I have written Java code, and on the right hand side I have written the C++ and the Python code, right? Now calculating in degree is a prerequisite for this algorithm, and I don't think it is a very complicated task. You can see that how I have calculated the in degree. For every node, whenever we have the adjacent neighbors, so all the neighbors will have an incoming edge, right? So I'm going to increase the in degree of every particular node. So this is how we are going to calculate the in degree. And now you can see that the pseudocode is the code is going to remain same as the pseudocode. We are first storing the node with in degree 0 here. After this, we are performing the BFS. So this is how we can solve the problem. What about the Python code? This is the Python code. So now let me talk about the time complexity of this algorithm. So you can see that all we have to do is to perform the BFS, right? So what is the complexity of BFS? BFS, the complexity of BFS is of V plus E. V is total number of vertices and E is edges, right? And the space complexity will be, this is the time complexity, and the space complexity will be, you can see that we are storing the in degree of every node, right? So it will be something O of V, right? Now I hope you have understood the problem. You have understood the concept. So this is all about this video. Thank you.